Today we will look at clock jitter and delta sigma modulators. Okay. So far we've been assuming that the sampling clock is ideal. In other words, every edge of the clock occurs, every rising edge of a clock basically occurs after exactly the same time t. Okay. For those of you who've done broadband ICs, you know that this is definitely not true. Okay. In practice, what happens is whenever you build a real oscillator, it so happens that this time t is not constant from cycle to cycle, but there is a random variation of this time t. Okay. This is like expecting your watch to take exactly 24 hours between one full rotation of whatever, exactly 12 hours for one full rotation of the thing. Okay. You can expect, because of random noise and thermal expansion and so on, that the time period doesn't remain exactly the same from day to day, right? So the first time this whole the needle goes through one full cycle is probably say 11 hours and 59 minutes and something, and then the next time is probably 12 hours and a few minutes and something. On the average, you can expect the time to be the average time taken for the full rotation is, you can expect to be about 12 hours, but there will be random variations around this 12 hours. Does that make sense? So, in other words, if I chop up these rising edges and superpose them all on the same graph, then if the clock was ideal, I should get only in this case something like this, right? Because all the cycles will, when I cut and paste on top of each other, the edges will all coincide. In practice, what happens is that there is jitter. In other words, these edges do not all line up. Okay, so there is random jitter, and like all random quantities, you characterize them by we assume that the mean of all these deviations is 0. All right. Sometimes the edge comes a little earlier. Sometimes the edge comes a little later. But you characterize therefore the mean is 0, but there's got some variance. Okay. So delta t. Okay. So RMS. Okay. So you can characterize, since it's a statistical quantity, the usual assumption is to assume it's Gaussian, and it's got some variance, which is characterized by the root mean square value. Does that make sense? It turns out that you can actually derive, what this variance will be if you know the details of the circuit that produced the oscillator are, right? So if you know the size of the transistors and the noise sources inside the transistors that when to make the oscillator, the clock is not coming from thin air, right? You have to make it. So the circuits that go into building the oscillator will have some random, all those devices have noise, which will in turn result in jitter in the clock that is generated by the oscillator. We will not get into all those details here. All that we will assume is that we have some clock, the edges are jittery with some standard deviation sigma equal to delta t RMS, and further we will assume that successive clock edges, okay, so ideally we would have expected something like this. So in reality, okay, there is some deviation here, there is some other deviation, delta T2. This is the deviation of the second edge from the ideal position. Similarly, you can come up with, the deviation of the nth edge is basically delta T n. We assume that these deltas are all uncorrelated. They are all random, of course, but we also make the additional assumption that the edges are all, the deviation, successive deviations are completely uncorrelated. So if you take, if you plot the path spectral density of the sequence of random numbers, it is white. Okay, so this is often called white jitter. Alright, so the question is to see what happens to the behavior of alright. So first thing to do is to, to go back to our the original modulators that we studied. These are discrete time delta sigma modulators, and in a discrete time design, where is the sampling done? The sampling is done up front, and then you process the whole thing, up front. I mean later in the modulator. So what happens now therefore is that if u of t was the input, alright, ideal input, the ideal output after the sampler must be u of kt, where k is an integer, alright. Now in practice what happens, the output is, this is the ideal one, it is actually kt plus delta tn. Okay, so the sampling instance is slightly screwed up because the edge of the clock is moving around. Does it make sense? So what is delta u of kt plus delta tn? This is approximately equal to u of kt plus delta tn times du by dt evaluated at k. Does it make sense? Okay. So if u was a sine wave, all that this equation is telling you is that if the input is rising fast, then if you don't sample at the right time, you make a larger error. Which is the error here? The error, this is the error due to jitter. You understand? And all that this is telling you is that if the input is varying fast, then a jitter in the clock will basically result in a larger error. Okay, and this is true whether the input is oversampled or not oversampled. Okay. Now, if the input is a sinusoid, what is du by dt? Du dt is basically a omega n cos omega n times t. Alright. So what is the mean square value of the error? It's the average value of delta tn du by dt. So this is a omega n cos omega n t sampled at kt. Alright. Alright. And since delta t and this are uncorrelated, what is this? This is nothing but e of delta tn the whole square times the expected value of a omega n cos omega t whole square. So that's the RMS value of, this the mean square value of the cosine, which is a square omega square by 2. Does it make sense? Okay. So what is this now? This is nothing but sigma, let me call this, I don't know what I call this in the slides, but sigma square of the jitter times a square omega n square by This is the mean square noise. What is the mean square signal? So signal power is a square by 2. All right. So what is the jitter limited SNR? Is a square by 2 divided by sigma square jitter times a square omega n square by 2. You understand? Which is basically 2 divided by sigma square jitter times omega n square. Oh, I'm so sorry. And as you can see, as the input frequency becomes larger and larger, the SNR goes down. Okay. All right. So in the oversampled situation, if as I said yesterday, what if I multiply two sequences, one of which is white, what happens to the spectral density of the sequence? It's also white. So in the oversampled situation, so this is the mean square value of the error due to jitter, and this is a white process, correct? So its spectral density is uniform from over the entire frequency range 0 to fs by 2, correct? But if in the particular case of an oversampled system, how much of this is falling within your signal band? I mean, so this has to be spread over 0 to pi, if you like, and pi by OSR is your signal band. So the in-band noise SNR, okay, is basically 1 over sigma square jitter times omega n square times OSR. Does it make sense? Okay. So that's pretty much what is said here. Yes, sir.
We sample after the integrator. We can also sample after the integrator.
No. This is discrete time, right? So this, by definition, the loop filter is only processing samples.
But if you do the analog thing.
Yeah, I'll come to that. That is jitter and continuous time delta sigma. That's what he's asking. But this is what happens when there is clock jitter in a discrete time modulator. Okay, does it make sense? All right. So let me, I think, probably open this with this PDF annotate. Not very intelligent. Okay, I think it's easier to do it from. Okay, so all right. So as I said, you can go and do the math, and this is what you get. All right. The next thing is what happens. So it's as you can see, evaluation of in-band SNR when the clock is jittery. In the case of a discrete time modulator, is quite straightforward. Let's see now what happens when you have continuous time delta sigma modulators, right? So in such modulators, where is the sampling happening? It's going to happen after the loop filter or before the ADC, right? So, and what is an ADC? What is the quantizer? The quantizer is nothing but an ADC and the DAC in cascade. And in an ideal quantizer, what you have is the same clock goes to excite both, defines the sampling instant of the ADC as well as the DAC, alright. So, in such a situation, the output is available right away, okay. So, the ADC makes a decision on the rising edge of the clock, the decision is made infinitely fast and conveyed to the DAC, and the DAC without any delay puts out a pulse which is proportional to the ADC output code, correct? But clearly this is not a practical situation. In practice, what happens? There are two things that we need to bear in mind. First, there has to be a delay between the ADC and the DAC, because the ADC samples, makes a decision, that decision has to be conveyed to the DAC, and whatever transistors in the DAC have to switch and produce a current or a voltage. So there has to be some finite delay between the ADC and the DAC. In practice, again, as we discussed in the last class, there is going to be in any real DAC has got mismatch, and to alleviate the effects of mismatch, what do you need between the ADC and the DAC? Joyce. What do you need between the ADC and the DAC in a practical, when you have a practical D to A converter? Yes, Rakshit. There is going to be a mismatch in the elements in the DAC. So what did we discuss yesterday was needed in between the ADC and the DAC to fix the problem?
Sir, some scrambler or
What is that block called?
DWM waiting.
Anyway. Okay. There are, any number of algorithms you can use in the middle, but all those class of algorithms is called what? Dynamic element matching. Okay. I don't know whether you guys come to class and sleep or, what you guys do. Yes, so it's mind-boggling. Anyway. So in practice, as I said, you need to insert some logic which will magically push all the error due to mismatch in the DAC unit elements to outside the signal band, and that's called dynamic element matching, and that's combinational logic which also has delay, alright. So that T delay represents the delay of all these together, and as I said, any practical clock will also have jitter. The edges will not be, what do you call, it will all not line up. There will be some random deviation of the edges from cycle to cycle. So let's see what happens to the due to jitter in the clock. First we'll talk about the ADC, what it does to the ADC, and then we'll see what it does to the DAC. Alright, so if a jittery clock is applied to the to the A to D converter, what happens? You can basically the A to D converter is sampling at the wrong instant, okay. So you can treat that as an A to D converter which is sampling at the right instant, but it is sampling some, not the signal it is supposed to sample, but some signal plus noise, where that noise is basically dVx by dt times delta t. Does it make sense? Okay. Alright. So now, you replace the A to D converter in the loop by, being sampled with a jittery clock by this model that you have for the jitter process, and you can see that lo and behold the error in the A to D converter due to clock jitter, okay, adds in the same place as the quantization noise, correct? So since it adds in the same place as the quantization noise, what happens to this Shankar? What is the effect of this E of n due to clock jitter? No, think, you're not sure, that's okay. What is the transfer function from E of n to the output? Yeah, so what is that in the signal band?
It's lesser than the signal band.
What is it at DC? 0. So in the signal band, I mean, so clearly the transfer function from E of n to the output is the noise transfer function of the loop, alright, and within the signal band the noise transfer function has got a very, very small gain. So since this adds in at the same place as the quantization noise, any error due to a wrong sampling instant of the A to D converter, what is your comment on, so what is the effect of that? It's all noise shaped, and so the loop takes care of everything, okay, so you don't worry about it. You understand? So, alright, the next thing is to look at what happens with the D to A converter. So the DAC is also now modeled by that the DAC has to be clocked, and the output of the DAC changes at every rising edge or falling edge of the clock. Okay, so if the clock is jittery, what happens? Ideally the DACs should have put out a pulse, say like this, alright. Because of timing jitter, what happens is that these edges could deviate from the ideal value depending on clock jitter. Does it make sense? The DAC output updates at the edges of the clock. If the edges of the clock move around, the DAC will update at slightly different times. It's quite straightforward. So the question is, what happens now to this? And as usual, we model the DAC output with a jittery clock as the output of a DAC with a clean clock plus some error waveform. Okay, you can always write y as x plus z. Okay, regardless of what x, y, and z are. You understand? So, the E1 of t now depends on the details of the clock jitter as well as the input code to the DAC. Correct? So, if you go and copy paste this model instead of the jittery DAC, what happens? It looks like this E1 of t, which is the noise waveform, whatever the error waveform, adds directly at the equivalently at the input of the A to D converter or of the modulator, right? And the transfer function from E1 of t to the output is the STF, which is pretty much 1 in the signal band, right? So here you didn't get lucky. Any crime committed by the DAC just appears as is. Okay. This is nothing that should surprise you people, because whenever you have a negative feedback loop, what happens? The forward path can be as screwed up as possible. As long as it's got high gain, it doesn't matter, right? It's only the closed loop performance is determined by the properties of the feedback block, and which is why you see big trouble brewing when the feedback block is screwed up either due to clock jitter or due to mismatch. Okay. The last couple of classes we spent on understanding what happens when there is mismatch in the unit elements in the DAC. Alright. And this class we'll spend time figuring out what happens in this jitter. Alright. And as you all know, there are several types of DACs. In every DAC is associated with a pulse shape. Alright. And this picture illustrates that. I think you are well aware of all this. This is on the left is shown the DAC input code, And for an NRZ DAC output, if the pulse shape is NRZ is an NRZ pulse, you can see that basically the output pulse is of the form. This is what happens. All right. On the other hand, if you have a return to zero DAC, what happens? The area under the pulses should be the same, so it should go up by a factor of 2 and then come back in the middle of the clock cycle, just like this guy here. Okay, this goes up to twice the value and comes back here. All right. So okay. So this is the actual waveform that's actually feeding into the loop filter. Okay. Now, yes sir. No. What will happen if there is dynamic element matching? Mismatch noise will change, which means what? Which part of the height of these pulses will keep getting averaged out. Okay, so if I put a code 2 and keep putting a code 2, all that it means is that sometimes for a code 2 the pulse is slightly different, the height of the pulse will change for this thing, but it will do nothing to the rising and falling edges. The rising and falling edges of the DAC are controlled by the clock. You understand? So this is the jittery DAC output. This is what happens when the edges of the DAC are, goofing off around their nominal value. So we'll have to figure out basically what happens to the error, right? Because that's the error. We are interested in the error that's being injected right at the input to the modulator. Is that clear, Pavan? Okay. So what is the error? The error is the ideal output minus the actual output. So what is this now? It's if the error has jittered a little bit, in other words, if this guy has moved around a little bit, then what will be the error? Look at the graph, picture and tell me. See, ideally this is what you should have seen. Actually what you are seeing is this character, say like this. Okay. So what does that mean? What is the error? The error waveform is simply this thin sliver here, which is the delta t multiplied by the change in the height, which is y of n minus 1. So this is in the special case of non-return to zero DACs. All right, the error waveform is dependent on the height of the step change in the DAC output multiplied by the jitter. Correct? If the output of the DAC is always constant, then there is no issue with jitter at all. Correct? It was supposed to be. If it was supposed to be like this and the edge jitters around, nothing will happen. The output will still remain the same. So clearly, whether it's an ADC or a DAC, jitter will screw you up. The most when the input is changing rapidly, and that makes sense. You understand? So is this clear to everybody that this is the error sequence? The width of the error sequence depends on the delta t. The height of the error sequence depends on the jumps between the adjacent codes. Is that clear? Okay. Now, what do you think will happen when you have an NRZ DAC? I'm sorry, return to zero DAC. For a return to zero DAC, the waveform will depend not on the successive difference but on the absolute amplitude. All right. And not only that, what about the width of the pulse? The width of the pulse is still delta t. Does it make sense? Okay. So without thinking any further, can you tell me in an oversampled situation, okay, in a multi-bit D to A converter, how does the output waveform look like? Let's say the input was like this, alright. In a multi-bit converter, how do you think the output will look like? Output of the modulator will look like? It will basically is jumping around the nominal, right? It takes only discrete levels, but the average must follow the input. So it will be some sequence straddling the input itself, and the jumps will be larger if. Okay, no. What else? For a given order, when will the jumps around the nominal be much higher? For a given quantizer and for a given order, when will the jumps be? There will be large jumps. No. Whether it's an RZ DAC or NRZ DAC, the output of the A to D converter will remain the same, right? The codes of the A to D converter will keep jumping up. No. What is the output of the A to D converter? Yeah, it is code, but what is the in the sigma delta loop? This is the A to D and this is the D to A, right? This is a loop filter. Alright, the output of the A to D is thankfully codes, okay? These codes are jumping around the nominal value, which is supposed to be the code corresponding to the input, correct? Alright, so for a to lead you to the answer, what I am expecting is, let's say I had a third order modulator, one with this auto band gain and the other one with a larger auto band gain. In which of these modulators will the output keep jumping more around the nominal? Pardon? So when the auto band gain is larger, the jumps in the outputs will be larger, correct? Because the output of the modulator is basically the input times the signal transfer function plus shape noise times quantization noise, right? Whatever, NTF times the quantization noise. Okay, so if the out of band gain is high, it basically means that the NTF has got a lot of gain at pi, which basically means that the quantization noise is getting selectively more amplified. High frequency quantization noise is getting more amplified, so the jumps will be much larger. Okay, so if you had a multi-bit DAC, do you think yn minus 1 will be large, or do you think yn will be large most of the time? Yn will be very large, because if you have a multi-bit DAC, what happens? Even though yn is changing, the cycle to cycle output changes by a very small amount. Okay, so based on this, can you conclude if as far as clock jitter is concerned, in a multi-bit DAC, do you think it makes sense to use a return to zero DAC or a non-return to zero DAC? It makes sense to use a non-return to zero DAC because the error here is proportional to yn minus 1, whereas here it is proportional to twice yn. Okay, and since we are dealing with an oversampled situation here, you find that the yn minus 1 is, most of the time much smaller. The mean square value of yn minus 1 will be much smaller than the mean square value of y of twice y of n. Is that clear? Alright. So to summarize, the error waveform in the DAC, which is the output of a DAC with the ideal clock compared to that with the jittery clock, the error depends on both the height of the transition as well as the number of transitions in the DAC waveform. Okay, non-return to zero DACs have a transition height of yn minus 1, alright, and one transition every Ts. Return to zero DACs have a transition height of twice the yn And how many transitions every TS? It's a return to 0 DAC. So it's going up and then coming back. Alright. So it's a double whammy. It's actually a 4x whammy because you have, first of all, the height is much more, and to make matters worse, you have twice the number of transitions. Okay. So without, it doesn't take a genius to figure out that return to 0 DACs are much more sensitive to clock jitter than when compared to a non-return to 0 DAC. Is that clear? Alright. So to give you a picture, the red is the input sinusoid, the grey stuff straddling the red input is the A to D converter output code, and you can see that the output code is jumping around the sinusoid. Alright. So if I kind of zoom into this circle here, I see that the A to D the code is jumping around such that the local average is the same as the input. Alright. Now if I zoom into one of these edges, what you see is that the clock is jittering, so the error made is basically the rectangle shown in grey. Does that make sense? Okay. So the next thing is, once you know what the error is, it's quite straightforward to figure out what the SNR is. So for in the case of a non-return to 0 DAC, the error injected every cycle is basically Yn. Ideally what should be pushed into the loop filter? Yn minus 1 times T. That's the charge going into the loop filter, correct? So, but right now you have an error which is Yn minus 1 times delta T divided by T. Does it make sense? No. Alright. So, pardon? It has to be dimensionless, no? Okay. Alright. So the mean square value of the error is the mean square value of this chap multiplied by the mean square value of this chap. The mean square value of this guy, let's figure out how to, the mean square value of this guy is very straightforward. I know the jitter in the clock, so the mean square value of that is 1 over T square times sigma square of the jitter. On the other hand, the mean square value of this guy has to be figured out. And what is the mean square value of this guy? We know that the output Y is nothing but the input sampled and goes through the signal transfer function. The STF is pretty much 1. So the output sequence is the input sequence plus, what is this? Shaped quantization noise. It's not quantization noise, but it is shaped quantization noise. Correct? So, and H of n is the impulse response corresponding to the noise transfer function. Okay? So, Yn minus 1 is V in of n minus V in of n minus 1. Correct? Plus EQ of n minus EQ of n minus 1 convolved with H of n. Alright? And due to oversampling, the input doesn't change very much. Alright? So Yn minus 1 is, for at least when the oversampling ratio is large, is pretty much the same as EQ of n. So this is approximately 0, or is very small. That's what I'm trying to say. Okay? So Yn minus 1 is pretty much this guy. It's just the first difference of the shaped quantization noise. Alright? Does that make sense? And and the quantization noise itself is a white sequence. That's what we assume in all our sigma delta theory, right? That quantization noise is additive and is white, and the mean square value is the RMS the mean square value of the quantization noise is the sigma square of the quantizer. So if the LSB size is delta, what is sigma square? Delta square by 12. All right. All right. So once you know this, what can you say about the? So this is like taking a white sequence, passing it through a filter of. So this is EQ of n. I pass it through a discrete time filter 1 minus Z inverse, and then pass it through the NTF of Z. Okay, and I am trying to find the mean square value here. Okay, so the mean square value of the output of delta y the whole square is simply you just use Parseval. You just use Parseval, and you can do this whole thing in the spectral domain. It is sigma LSB square by pi. That's the spectral density of the uniform quantization noise. Sigma LSB square is distributed from 0 to pi, right? So that is the spectral density multiplied by 0 to pi 1 minus e to the minus j omega NTF of j omega the whole square d omega. Okay, so the in-band noise due to jitter is nothing but sigma delta y whole square times the mean square value of the jitter, right? So it's sigma square delta ts by t square times this is sigma dy the whole square.
How can we say it's uniform here? Like we just multiplied by 1 by OSR. We just multiplied by 1 upon OSR to calculate in-band noise.
Correct.
But we don't know the shape of noise.
No. See, please note that this is white. What do I say? The jitter is white. So what will be the spectrum look like? What will be the shape of the spectrum look like? No, it's not white. It's shaped noise, right? All right. What is this? This is white. So if you multiply a white sequence with any other sequence, as long as the two sequences are not correlated, right? You have white. The result is white. Okay. So the mean square error due to jitter is this guy, and this is a white process. All right, which basically means that the mean square value is spread across 0 to pi. We are interested in only the in-band noise. So the in-band noise due to jitter is basically sigma delta ts the whole square by t square times this stuff divided by the oversampling ratio. Does that make sense? Okay. So let's stare at this expression a little while and figure out, what this means. The first thing is that, what is the shape of this chap? This is shaped like this. Okay. So where is the most of the contribution of the integral coming from? It is coming from around here. All right, just one observation. So as far as choosing an NTF, if you go on increasing the outer band gain, what can you expect for noise due to jitter? Must increase. Why? There are several ways of looking at it. One way is to look at this formula and say most of the gain is coming from, most of the integral is coming from stuff at high frequency, that is frequencies around pi, So if the out of band gain of the NTF increases, then you will have more in band noise. Is that clear? Okay. All right. What is a more commonsensical way of looking at it?
The noise will be very much different. Because the two noise will be very
I don't understand what you
say.
say.
Different, very much. They differ very much.
Yeah.
They change very much.
Okay. So a time domain intuition of getting making the same conclusion is that if I increase the out of band gain of the modulator, what can you expect for the output waveform? The jumps will be much larger in magnitude, correct? And every time there is a jump, you know that you are adding some error. So an increased out of band gain for the NTF will result in more jitter noise. You understand? Does it make sense? So if you increase, if you increase out of band gain, what happens to the quantization noise? Shankar? Yes, it will decrease, correct? So if you get too over enthusiastic and say I want to reduce my in-band quantization noise, go on reducing my in-band quantization noise, what will happen to the quantization noise will definitely reduce, okay? But what happens to the jitter noise? The jitter noise will increase, okay? So there is a, like most real world situations, there is always a trade-off between something and something else. So if I plot the out of band, if I plot the total in-band noise, okay, as a function of out of band gain, what do you think will happen? The quantization noise will go down like this, alright. The jitter noise will go up like this. If I add the two, that's the total in-band noise, that will be something like this. Okay. So, often there is a sweet spot for choosing the out of band gain. You understand? So, we have understood this, and so for a given noise transfer function as well as a given NTF, for a given order and for a given noise transfer function, if I reduce the resolution of the quantizer by 1 bit, in other words, I had half the number of levels as I had before, what can you say about the in-band quantization noise? So the in-band, the signal to noise ratio, signal to quantization noise ratio will go down by 6 dB. Factor 4 in power is 6 dB. Alright, which corresponds to 1 bit resolution. What do you think will happen to jitter noise? If the resolution of the quantizer has gone down by a factor of 2, by 1 bit, which is the number of levels have gone down by a factor of 2, what happens to the LSB size? The step size of the quantizer is increased by a factor of 2, which means what happens to the jitter noise? It will increase by 4 times. Alright? Because the step, when you had a 16 level quantizer, the output of the ADC is doing stuff like this. When you have an 8 level quantizer, the step sizes have all increased by a factor of 2, so the jumps have all doubled in height. Okay? Which means that the in-band sigma LSB square has gone up by a factor of 4. Okay? So multi-bit operation has this additional benefit that increasing the number of levels in the quantizer to begin with, alright, has the additional benefit of being less sensitive to jitter. Is that clear? So we can do an example calculation. Let's say we have an audio modulator. So the bandwidth desired is 24 kilohertz. Assume a 4-bit quantizer. Oversampling ratio of 64. So this results in a sampling rate of about 3 megahertz. Let's assume that the quantizer input range is 2 volts. Okay. So the LSB size is 2 volts is the full scale. So the step size you divided into 16 steps. So the LSB size is 2 by 16. So the mean square value is nothing but delta square by 12. This is alright. So if I assumed 100 picosecond RMS jitter, alright, and an NTF with an out of band gain equal to 2.5, alright, then I can go and compute the integral, alright. I mean, see, okay, anyway, so this is a third order modulator, right. So I can go and compute the integral, okay, and it turns out that when I do the maths, this is what I get, okay, and for this modulator and this out of band gain, it turns out that the maximum stable amplitude of the loop is 83% of full scale. So the peak sinusoid that I can put into the ADC before the quantizer gets into saturation and bad things start to happen is 0.83 volts. So the signal to jitter noise ratio is 20 log the peak signal amplitude, okay, I mean 20 log the RMS signal amplitude divided by RMS noise, okay, and that turns out to be about 113 dB. You understand? So the conclusion is that 100 picoseconds RMS jitter is not an issue if you wanted to realize a 15-bit modulator for digital audio, okay. You need an SNR of in-band SNR of something much larger than 90 dB or so, okay. So if there is 100 picoseconds RMS jitter, this will basically mean that you have, I mean the noise jitter is 113 dB, which is about 23 dB smaller than the SNR you are trying to hit. So clearly jitter is not a limiting factor. Does this make sense? Okay.
Sir?
Yes, sir.
So when we specify the MSA, so that is
No, you don't specify it. You find out once you know the NTF, you can go and find it.
yes.
I found out and it turns out to be 0.83 volts.
So this 0.83 is peak to peak.
No, it's a 0.83 volts peak.
Sir, the quantize.
The quantizer goes from 1 to -1,
Okay.
2 volts input range, and you fit. Ideally, it should have been 1 if it is full scale, but clearly the MSA has to be smaller than full scale, and it's 83%. That's what it turns out. Okay, you understand? So if the NTF happened to be 1 minus Z inverse the whole square, it's second order modulator with this thing. Can you compute what happens to the jitter? What is the integral? It is 1 minus the magnitude of 1 minus Z inverse whole cube. Okay. Square. Alright. So no, it is not omega to the power 6. You have to integrate from 0 to pi, not from this thing. Okay. So what is the easiest way of doing this?
Take the sum of
Pardon? You do it in the time domain and use Parseva. Right. So integral 0 to pi of this, integrated over the entire band, you can simply do the whole thing in the time domain. Okay, it's much easier. You understand? So the bottom line is that clock jitter is a problem in both discrete and continuous time delta sigma modulators. Okay, and in a continuous time modulator, it's the DAC which is the problem, not the ADC, because the noise due to the ADC is largely shaped out of the signal band because it adds exactly in the same place as the quantization noise. The DAC noise, on the other hand, directly adds at the input. Okay, so you can't push it out of the band. The next thing is that the DAC pulse shape influences the jitter performance of the modulator. Specifically, an NRZ DAC is, if you have a multi-bit quantizer, a non-return to 0 DAC is a much better choice than a return to 0 DAC as far as jitter is concerned. Okay, because in an NRZ DAC there is only one transition every cycle, and the height of the transition, which is proportional to the, and you know that the error introduced is proportional to the height of the transition, is y of n minus 1. Okay, and so the height of the transition is smaller, and there is only one transition every clock period, whereas in a return to 0 DAC the height of the transition is double, alright, and the number of transitions is reduced by a factor of 2. Sorry, the number of transitions increased by a factor of 2. Alright, and you know the height of the transition is also not proportional to the difference between successive codes. It is the height of it is the absolute height of the successive of that particular code. You understand? So why do you think return to 0 makes sense at all then?
Delay is there from ADC to text, and delay we model using feed-forward path.
Yeah.
Model here because delay is variable. We had a feed-forward path dependent on the delay.
Yes.
So we can't model if the delay is not predictable.
Oh, please note that this jitter is all sub is a very very small number. So the argument he is making is that isn't clock jitter a problem also because it kind of varies the noise transfer function of the loop, since you can think of it as a change in delay, but this delay will be very very small compared to the period of sampling. If this jitter becomes comparable to the rate at which you sample, alright, then you're in deep shit. Okay, so it's that's not what happens in practice. So for example, to get 15-bit operation we said 100 picoseconds RMS and 3 megahertz clock rate. For a 3 megahertz clock rate, what is the time period of the clock? It's 300 nanoseconds, and the jitter is sigma is 100 picoseconds, 3 sigma is 300 picoseconds. So you can see that it's a factor of 1000 smaller. Okay, so excess delay is not the problem. Why do you think so? We see that NRZ is like very bad with respect to clock jitter, alright, but still why do you think why do you think it could be it's so bad? Why bother about talking about it at all?
With more transitions and more high frequency components, so STF will suppress the high frequency components.
Yeah, so what?
Sequence will pass through STF.
Yes, but we are only interested in the in-band components, right?
Yes, sir, but we have anti-phase transitions in a sequence in RZ.
Yes.
So it will have high frequency components more than.
Yes. Yes. Okay. So what?
So more part of it will be suppressed.
Yeah. So what? The in-band. As far as the in-band performance is concerned, and if you go on and design the loop filter properly, whether you have an NTF, whether you have an NRZ DAC or a return to 0 DAC, the NTF must be the same. All right. So what is the advantage of a return to 0 DAC? We have done this before.
It's more linear as compared to
So as we discussed early on in this course, if there is rise time fall time asymmetry, then a return to 0 DAC is by definition is linear, alright, because the edges are screwed up. It's screwed up, the screw up is in proportionality, right? So if you put 1, I will get a screwed up pulse. If I put 2, I will get exactly twice the same screwed up pulse. So by definition it's linear. On the other hand, if I had a NRZ DAC, that's no longer true. Alright. So this is what is the difference between NRZ and RZ DACs. Okay. So which is why it makes sense to discuss it, because it is NRZ, return to 0 DACs do have some attractive properties. Alright. So that completes the discussion on, we have taken basically a first order modulator and figured out all its problems, which are problems with the loop filter, finite gain, offset and finite bandwidth, excess delay in the loop, okay, RC time constant variation, as well as clock jitter, okay, and as far as the DAC is concerned, we figure out what happens when there is mismatch. So this covers all the non-idealities that you can have in a continuous time sigma delta modulator. The only thing left is to figure out what? How it, I mean, so most of all these properties will carry over. Jitter, dynamic element matching and all that is the same effects for higher order modulators. So the only thing that we need to do is to figure out how to synthesize the loop filter to realize what people? Higher order NTS. Okay. So we'll do that tomorrow, and I think hopefully I will wind up.